Okay, so we've looked at lots of mechanisms in SQL. Now I want to talk a little bit about some abstraction mechanisms that you can use when you want to put together a whole bunch of queries to solve a particular problem that is too complicated to write as a single query. Okay, so let's have a look. So I think I've said this a little bit when I first introduced writing SQL queries, but if you've got some complicated information request, it's often possible to break the query into a collection of smaller queries, and in particular start from sort of go in reverse order and look at, I could solve this problem really easily if I had a particular table that had certain properties, and then write a solution in terms of that ideal table. Then that becomes a slightly smaller problem to solve. So how do I produce that table? Then I might need I can treat that the same. I can say, all right, it would be really easy to produce this other table if I had another table, and so on and so on. So you can break the query into a collection of smaller queries and build them one on top of the other until you eventually get to the top level query, which, like a main program in a well-designed C program, would be relatively small and make use of functions that called other functions that called other functions. So that's the analogy. All right, now it turns out there are a number of different ways that you can glue queries together in SQL. Views, we've already talked about. You can write subqueries in the where clause. I talked about that briefly. You can write subqueries in the from clause, which is something we haven't looked at yet. And there's also a with clause, which allows you to package up queries. And the subqueries in the where, from, and with are basically ways of avoiding writing a view to solve a problem. Sometimes that's actually not possible because, for example, in the where clause, you may need information from the main query to be pushed down into the subquery, and we've already talked about those correlated subqueries. All right. So let's take a look at a problem that we want to solve and look at a number of different ways that we could solve that problem. All right, so we want to get a list of low-scoring students in each course, where low-scoring means the mark is less than the average mark. All right, so we've looked at partitioning as a way of adding a property of a group to the end of each tuple in that group. So basically, the first thing we're going to do is we're going to produce a bunch of tuples that have, like the enrollments table, course student mark, but appended to each tuple we also have the average mark for that course. And then it's pretty easy, we just select those tuples where the mark is less than the average mark. Okay. So doing it with a view, you should all know how to do that. We just use our partitioning query and produce a view that has those attributes. And then we use that view and simply use that condition on the view. And that's going to give us the correct set of students. Here we're just taking the course, the student, and the mark. We're not taking the average. Maybe we could. That might be a useful thing to do, to find out how far below the average they are. All right, well, we know how to deal with views. We can create a whole bunch of views and we can put them together in our main query and write conditions. We can do joins on the views, and we can write conditions on the various attributes of the views. So to some extent the views look like virtual tables, and in fact the from clause could contain real base tables as well as views. Views are useful if we actually need to execute this query lots of times. If it's something that we're going to do just once, then maybe some of these other strategies might be more useful. So here's another example, putting the query into the from clause. Okay, normally what we have in the from clause is a name of attribute of tables, possibly joined together, possibly some views as well. But here what we're doing, we're actually defining the table in the from clause via a query, and this is our favorite query where we're getting the students who have marks, well, who have course student mark and the average mark for the course. And then we're giving a name to that, which happens to be the same name as we gave the view, and then we're using the same condition to extract just the relevant tuples. So basically this is going to do something a lot like the view did. It'll execute that query, it'll give it a name, and then through each of the tuples of that query, we'll make this test, and any tuples that satisfy that will end up in the result. So basically what it does, it saves you having to define a view. And here's the general way you can use queries in the from clause. So you can have a query, give it a name, have another query, give it another name, and then kind of treat those names almost like tables. And then you can run the rest of the where clause using the attributes contained in these tables, virtual tables. To make this work, you can't just plonk a query there and not give it a name. You have to give every one of the subqueries a name. And the subquery tables, you don't actually have to specify a list of attributes, and if you don't, they just inherit the set of attributes from the attributes in query 1, for example. Okay, another way of achieving the same effect is to use a with clause. So basically a with clause allows you to define a temporary view, if you like. So here you're giving the name of the view, here you're giving the definition of the view. Once again, it's our partitioning step. And so once you've defined the view like this, you've got a name, and you can use that name in the from clause as if it was a view or a table. And then of course we're testing the where condition. And oops, looks like I've done a slightly different thing. I've actually added the average to the output tuple, whereas the previous ones didn't do that. Alright, so once again giving a name to a query, and here you can specify attribute names at this level. So by the time you reach the select statement, so the with is actually a part of the select. So you've got all these definitions in the with clause. By the time you reach the select clause, you can kind of think of them as tables and start using them as if they were tables. Now, with allows you to do something else. Recursive queries. Interesting thought. Hadn't considered that queries might be recursive, you say. Right, now recursive queries weren't actually part of the original SQL standard, but they were added in later standards. And I think maybe SQL 1999 might have been the first one that included recursive queries. Alright, so how do we structure these recursive queries? Well, like recursive functions, you have to have a base case and a case that does the recursion, the recursive case. So here we're defining a recursive query R, which has some attributes. The base case is the first thing you write, and what you do is you take a union of the base case with the recursive case. All sounds a bit weird, but I'll show you how it's actually computed in a moment. And then, having done this, you've got a table called R, and in the select clause, so once again we're using a with. You've got a table called R, and you can treat that like a regular table. Here I haven't bothered putting other with tables or with views, or whatever you want to call them. But so we've only got a single table R here, and then we've got conditions on that table involving the attribute. Now, places where these are actually useful is if you've effectively got a graph structure encoded in a table. And the way that's going to work is you'll have tuples, which are parent tuples if you like, and then the children tuples will have foreign key links to those tuples, and then you can have children of the children who have foreign key links to the child tuples, and so on. That was the way I described that. It was a strict hierarchy, but you can also have an arbitrary graph. Representing arbitrary graphs like that leads to things that aren't super efficient in SQL, and so people have invented specialized graph databases for efficiently processing or representing graph data in a more efficient way and processing it more efficiently. But you can do it in SQL. So once again, just a reminder, we're defining a recursive function in terms of a base case query and a recursive query, if you like. Right, so the base case doesn't include R, it's not recursive, but Q2 is the recursive case, so it has to include R. Alright, so the notion is that we've got some temporary tables. We've got a table called working, got a table to hold the final result, and we populate both of those tables initially by evaluating the base case. So in contrast to the recursive functions you would have seen in something like C, which are basically top-down recursion, this is effectively bottom-up recursion, starting from the base case and gradually building on the base case to produce the final result. Okay, well, the working table tells you what else needs to be done effectively, what tuples are remaining to be investigated, if you like. Once that table becomes empty, then your recursion, or your recursion is done. Alright, so what you do at each step is you evaluate Q2, but instead of using R, you use what's in the current working table. And that'll give you a temp result. So you subtract the current overall result from temp. That gives you a new version of temp. And that's basically to get rid of stuff that you've already got. So here we're talking set difference. And then we use union to take the temp result, which are effectively the new tuples that we just generated, and add them into the result. And then we set temp to be, or set the working table to be equal to temp. Right, I said temp are the new tuples that you just generated. If you don't generate any new tuples, then basically that means your recursion is finished. You've reached a fixed point. And so we go around the loop again. Now working will be empty because we didn't generate any tuples on the last iteration. And so basically that's effectively the semantics that does. It generates new tuples until we don't generate anything that we haven't already generated. So that's effectively what you're doing in there. Right, let's have a look at a concrete example. I mentioned that we've got parts and subparts and sub-subparts and so on. And what we want to do, we want to count the number of subparts in a given assembly, or in a given part, if you like. So our table looks like part, subpart, which is a child, and the number of those subparts that appear in the main part. Right, so this is how we'd write the recursion to make sure that we can get all of the parts that are included in the top level part. Right, somehow we're going to have to pass in the top level part. Potentially we know what that is and we can just put its value there. Alright, but we're defining a recursive view, if you like. Alright, so our included parts gives us a subpart, a part, and a quantity. So notice that we've reversed the order there. Alright, first thing we do is we grab the immediate subparts, and that becomes our initial working set, or our initial result set, if you like. So all of the immediate child parts of the original part. And we get the quantities of each of those. Alright, the recursive step takes the included parts that we've generated so far, joins that with the parts table, and basically looks for subparts using the included from the included parts table, and using that will generate more tuples, potentially generate more tuples of the form subpart, part, and quantity. And we'll keep doing that until we've reached all of the included parts in the original part assembly. So there are no more parts that have child parts, if you like. Alright, so that gives us a bunch of parts, subparts, and how much of each. So what we do, now we may have subparts occurring multiple times, so we have to do a group by subpart from this included parts view or table, whatever you want to call it. It was recursively generated, and then we'll take the subpart and we'll add up the quantities for all of the instances of that subpart, and that'll be the total quantity for that subpart. And that gives us our final result. So you can do recursion in SQL. There are not a lot of contexts where you'd actually use it, but it's interesting to see that you can do it nonetheless. Alright, so that's a quick look at various forms of abstraction that you can use. You can use views, you can use subqueries in the from clause, you can use subqueries in the where clause, and you can use with to effectively give names to subqueries.